Ok, senhores. Próxima palestra. Bom, não vou nem comentar a zoeira com o meu servidor, né? Sacanagem. Travis, por favor. Pessoal, eu não sei se vocês conhecem o Travis Goodspeed. O Travis é um dos mais famosos hardware hackers que tem aí no mundo, né? Basicamente, nós temos os dois mais famosos aqui na conferência, o Travis e o Mike Osman. Ambos estão aqui, tá? A palestra é extremamente brilhante e quem gosta dessa área de hardware relacionado a software e o que você pode fazer quando você muda o hardware pelo que você esperava do software, vai adorar essa. Boa palestra.
All right. Howdy, y'all. Are we ready to begin? Okay. Does a shot? Does anyone need a shot? If someone could bring me an Apple power supply, that would be handy. Okay, so today I'll be telling you about the Southern Appalachian Space Agency, which happened when I was drunk on eBay and purchased a satellite dish that was surplus from the United States Navy. I had this delivered to my farm in Tennessee, which is where Jack Daniels is made. Which, coincidentally enough, was what I was drinking when I bought the satellite dish. And then my friend and I repurposed this satellite dish to be able to track satellites that are in low Earth orbit. Most satellite hacking is done against satellites in geostationary orbit because they're a steady target. So if I take a ham radio and I aim an antenna south from Tennessee, I will hear Portuguese over the radio because Brazilian truck drivers are reusing American satellites from the 1970s in order to bounce traffic across their truck driving routes. But I wanted to track the satellites that were moving very close to the ground, the satellites that are moving very fast in the sky and that move through the sky so quickly that you can't leave an antenna pointed at them because they'll move through the entire sky in 15 minutes. Examples would be the International Space Station or the telephone satellites, so Iridium and Globalstar. These move through the sky very quickly, and you need custom hardware and software to track them. The software that's available for tracking them isn't very good, so I had to rewrite my own from scratch. And my friend Colin Mulliner demands that we have a bet going as to who can put more dinosaurs on stage. So I score 1 point. I did this work thanks to the help of Fabienne and Sky T, two friends of mine from Berlin. And it sort of built upon work from Adam Laurie and Jim Giovetti, who did earlier work in geostationary satellites, the ones that are so high that they stay in one space relative to the Earth. And also to the good neighbors at Dartmouth, who were around for a lot of the conversations involving this. Now, you can't have a space agency, in my case, the Southern Appalachian Space Agency, without a mission patch. And this is our mission patch. It's based upon my people's native culture. We have lots of like cinder blocks and cars in cinder blocks, and it's traditional that you'll have many unused cars in your yard in Tennessee. So I have here cinder blocks beneath my satellite dish, and this is factual. The dish really is sitting on cinder blocks. On the right, you have an alien. There are these little green men about this tall. We call them boogers. In the background, it's kind of hard to see. Right about there. That's a moonshine still, because it's traditional to make whiskey at home where I come from. In the sky, you can see some space garbage and the International Space Station, and there's a glove and a banana. Because they have to shoot their garbage downward or it stays in the same orbit that they're in. So that orbit can get cluttered as pieces break off. And then on the left, there's a man with a neck beard and a shotgun. And he has the shotgun to defend himself from the booger on the right. So at at Berlin Sides last year, I gave a lecture on reverse engineering the SPOT protocol. Have any of you seen that movie where the guy was hiking and the rock fell on his arm and he had to cut his arm off to get away? He really would have liked to have some cell phone reception. What SPOT does is it allows you to send a message from your cell phone up to a satellite, and then the satellite redirects the signal to the internet. So even if you don't have a cell phone signal, you can still transmit a message from the middle of the desert or from the middle of the ocean. So I reverse engineered this protocol. First, I reverse engineered the Bluetooth that's used to allow the phone to talk to the SPOT. And then I reverse engineered the satellite link, which runs at 1.6 gigahertz. It is completely clear text, it is unencrypted, and if you have a recording of this signal, it's very easy to parse it and to interpret it. It contains the serial number, GPS coordinates, and whatever text message you send up. So if you say like, hey mom, I'm all right, I'll get that. If you say, oh dear God, the rock is crushing my arm, please send help, I'll get that. This is a photograph of the device. It's about that big. And these are really easy to program. Their Bluetooth protocol is very simple. And they're easy to reverse engineer. To reverse engineer the, coffee is complicated. To reverse engineer the Android application that initially controlled this, Android, at least the Cyanogen mod ROMs, contains a tool called HCI dump, which will dump a log of all of the Bluetooth traffic that that particular device has had. This is important because Bluetooth is terribly difficult to sniff externally, but if you sniff it from one of the devices that's supposed to be in the conversation, you can get a very good recording. And on the right is a screenshot of what the output looks like. So you can get Google Map results of where you were. In this case, I was in Philadelphia walking west across the Schuylkill River. When you have the recording, what happens internally is that the SPOT sends a long series of a pseudo-random code for either a 0 or a 1. But when it switches between these, there's a little pop on the radio. So when you look at the recording, which goes downward in this recording, you have a number of zeros first, and then whenever there's a switch from a 0 to a 1, you have a pop. Those are the little circles. And the circles happen between the bits. The circle is not a bit itself. So the status was that I know the protocol, and I can sniff the uplinks, but I want the downlinks. I don't want to see people in my same city talking to this satellite. I want to see people on my same continent talking to this satellite. And the way to do that is to sniff the downlink. But that requires a satellite dish, and it requires a moving satellite dish, because these satellites move through the sky very, very quickly. So I took a look at Adam Loy's tools for playing with geostationary satellites, which he published in 2008 and in 2010. He used a KU band receiver with a DVB-S television card. This is the same sort of setup that you would use for receiving satellite TV in Linux. And then he made the television dish move by a dissect motor. A dissect motor can only move left and right. It's not able to move up and down. And his tool is available. It's called SatMap. It's at this URL. This is a photograph of his feed scanner. What this tool is doing is it's trying every frequency on the current satellite in order to look for video. And this movie playing on the left is coming down from the TV satellite. You can also make maps this way. I made this map by moving one of my dishes left and right, and then recording which frequencies are being used. So the x-axis is the azimuth, and the y-axis is the frequency, and wherever you see a dot, there's a transmitter. You can see that satellites which are next to each other try not to use the same frequencies. So as you move from left to right, there are gaps. And you'll also see that some frequencies are just like a little pinprick that's away from the others. Those are, I think, are physically separate satellites that are just near each other. And at each step in azimuth, I'm seeing about 3 degrees of the sky in width. And if I go much further east or west of this diagram, my dish is misaligned. Because the geostationary satellites form a sort of ring in the sky. This is called the Clark belt, after Arthur C. Clarke. Because it's a curved shape and I can only move left and right with this dish, I can't see things that are in the wrong position in the sky. So the advantages of it are that there's cheap hardware available. You can just buy a kit to run Adam's tools. You'll pay about $250 US. The protocols for talking to these motors are standardized. So your machine doesn't really care what brand of motor you have. You don't have to do much more than simple rewiring. And you get TV signals with video feeds. So it's really easy to point at an incoming signal and say, hey, I got that. You'll also find weird signals, like on the news when they interview people. Very often the interviews are bounced over this network. So you can actually watch the interviews live, and you can sometimes see embarrassing footage where people say things when they think they're off camera. And there are also TCP/IP packets going across this network. So if you sniff by this sort, you can actually catch internet downlink traffic, which is sort of like sniffing half of a Wi-Fi connection. You see what the access point says to the user, but you do not see what the user says back to the access point. But there are disadvantages. It only works with geostationary satellites. So unless it's 24,000 miles in the sky, exactly, and staying in the same place, orbiting once per sidereal day, exactly, you're not going to be able to receive it. And it's very slow, very inaccurate tracking. So in my diagram before was measured in ticks and not degrees on the x-axis. That's because my motor isn't accurate enough to properly tell me how many degrees I've moved. I would like to be able to move a fraction of a degree perfectly accurately and repeatably, and you can't do that with dissect motors. You're also limited to standardized signals. You'll find TCP/IP, you will find video, and that's it. And a lot of it is encrypted and becoming more encrypted. And the general rule of cryptography is that satellite TV providers are the only ones who do it right. They lose a hell of a lot of money whenever anyone can make fake receiver cards. So they've invested a fortune in preventing you from receiving these encrypted signals. So I bought a satellite dish. This is my dish being removed from a Navy warship. It's a civilian dish, but the ships have to have all sorts of communication methods. So you might also be able to find one of these same dishes from, say, a high-end yacht or a cruise ship. My dish is a Felcom 81. It's a 1-meter dish intended for use with Inmarsat. It has stepper motors for azimuth, elevation, and tilt. Because the idea is that this dish would be put at the top of a ship's mast, and as the ship rocks, this dish can correct for the rocking. I paid $250 for this on eBay. It cost me $200 for delivery, but luckily the guy I bought it from wanted an excuse to drive near where I was. If not, I would have had to pay a king's ransom in airfare to have it delivered. So I'd recommend that if you wanted to repeat this work, you find a port city and someone who repairs yachts and try to buy a dish from them cheaply. And it has spinning gyroscopes for stability. So the way that this thing can tell how the ship is rocking beneath it, because this was designed before the iPhone. This was designed before MEMS was available. So you couldn't just have an electronic accelerometer. You had to have gyroscopes. And these gyroscopes had to have spinning wheels in them. Now, after these wheels spin up, the dish needs to know exactly how far they've turned. But a gyroscope doesn't tell you that. It just tells you that you're too far to the left or too far to the right. So it actually has motors that move just the gyroscopes. so that it can measure the difference between the gyroscope and the dish in order to be able to turn a specific and known number of degrees. Unfortunately, the software that it ran was closed source and antique. This runs on an 80286 chip internally. It can't even run Windows 95. So I built my own software to run on it, which I call the Sasa Framework, or Southern Appalachian Space Agency. It's designed for tracking low Earth orbit satellites, and it produces the azimuth elevation and tilt values that the dish needs, but there's no reason why it's limited to tracking the things that are moving. So my software also tracks stars. I can track deep space probes. This tracks Voyager 1 and Voyager 2. And I threw in a software-defined radio. So I can record a strange signal and then demodulate it later, not really caring what it is at the time that I record it. And this is very important because it allows me to separate the problem of finding the signal from the problem of decoding the signal. I can give a copy to Mike Osman, who's better at doing software-defined radio than I am, and he doesn't need to have his own dish in order to get the recording, or in order to build his own receiving software. This is particularly useful when identifying unknown downlinks. And I run the entire thing through Linux machines that are spread around the house that holds the satellite dish. So I have a Beagle bone inside of the radome. This is physically strapped to the dish, and this moves with the dish. This has the software-defined radio, this has the motor controllers, but it's not powerful enough to do the software-defined radio parsing. So it sends all of that data in the raw over Ethernet to a server inside of the house, and it's the server that actually does the software-defined radio decoding and recording. Because the server can have as much storage as I care to plug into it, but anything inside of the radome has to move with the dish. There's too much weight, and if the weight gets above a threshold, the dish will become inaccurate. And I run the entire thing through Postgres. So if you were able to do a SQL injection exploit against Sasa, you could physically move this dish. By doing the right malicious update statements, you could cause it to wrap its umbilical cord around and sort of hang itself. And the SQL framework makes it really easy to give the thing orders. So if you want to know where my dish is pointed, you run select as L, that's azimuth and elevation, from the position table, and that tells you where you are. If you want to aim at, say, Voyager 1, you do an update statement, update target set name equals Voyager 1, and then the targeting daemon will begin tracking that object. At the moment, I'm using a Realtek SDR for the software-defined radio, but I hope to move that over to a HackRF soon. I use an iBot board for motor control, and I have an inertial measurement unit from VectorNav. Because today, oh, damn Tweety boxes. Today you can afford to have an inertial measurement unit, whereas when this dish was designed, an IMU is the sort of thing that you would only have in, say, a cruise missile. Now we all have them in our cell phones. This is the dish itself being worked on. This is the rear view. You can see that there's this central stalk here, and that there are motors based around it. So from this position, I could have the entire dish turn left, the entire dish turn right, or have the dish raise up or fall down, or I could have it tilt. On the central stalk, I have all of the devices wired up, and they're connected to each other by USB, and then connected to the household network by 100 megabit Ethernet. The red board on the side is the motor controller. The green board is a standard commercial USB hub. The white board is a BeagleBone, which is an ARM system-on-chip computer that's about that big. The stepper motors are undocumented, but there are only so many different types of stepper motors. There are 6-pin stepper motors, and there are 4-pin stepper motors. These are 6, but if you ignore the inner 2 pins, then it's easy to connect them to the stepper controller. The stepper controller is an IBOT board. I is German for egg, and the pairs of connectors at the top, there are 8 pins in total. Those are for motor 1 and motor 2. This is what the board was originally designed for. This was a toy that paints Easter eggs using a pen and moving the egg around. But this same motor controller is powerful enough to move that large satellite dish because of gear reduction. The dish itself has small motors that are connected to pulleys. The pulleys reduce the movement but increase the torque so that the small motors on the satellite dish are enough to aim the dish. As a backup, in case I forget where my dish is, I have a webcam on the back. And this white thing here is the radome. That's my brother's lovely car on the left. That's my father's lovely truck on the right. This radome has like a white inside, and the sunlight comes through it just a little bit because this is fiberglass. So we painted the radome so that the webcam can look out at the radome, and then if there's a software bug, or if one of you were to be a jerk and to run a SQL injection exploit to make my dish forget where it is, I can repair its positioning remotely. And this is important because I built this in Tennessee, and Tennessee is a long way away from any place with a good airport. So, it takes me a long time to get to Tennessee, and it takes me a long time to leave. By painting the radome like this, I can remotely repair it when simple things break. The software also runs through this Postgres framework. So this is a photograph of Sasa Commander, which is the live command and control utility. All of these red entries are satellites, and the green one is the satellite that's being targeted. The crosshairs show at which point in the sky the dish is aimed. And as these satellites move through the sky, whichever one is being targeted will be followed by the dish. So GOES 3 sort of hovers in the same region of the sky, but it moves up and down a lot. And I can just leave this alone for hours to follow that target. Could we dim the lights in the front just a bit? These screenshots are hard to see. So these white pieces in the background, those are stars, and I can actually project the same star map onto the Sasa view as you would see in the night sky. So if you're using this at night, you can look up in the sky and actually visibly see by constellations which part of the sky you're targeting. That's a bit better, thank you. Now, this can also do a polar view. So in this case, you're seeing like a top-down view on the satellite dish, whereas here you see a first-person view, like as if you were looking out from the dish. By comparing the two, you can start following things that are harder to track. For example, Polaris is the North Star. It's just in the center, directly up from the center of the circle. That's either at the extreme left or the extreme right of the standard view. So the polar view allows me to see that. This can also run on cell phones. So this is my Nokia N900 controlling the Sasa dish. And in this screenshot, I'm connected over Wi-Fi, but in places where there's good 3G service, I can actually develop the dish's software on public transportation. So a significant portion of this development I did from the subway in Berlin. They have good network connectivity there, so I would just SSH over to the server, open up an Emacs session, and begin hacking away, and I can do that remotely. By tunneling the Postgres process, then my same client could run. I also have this running on my Nokia N900, which is terrible for development because, my Nokia N9. This is terrible for development because it doesn't have a keyboard, but it's really cool to be able to just pull out a cell phone and order the dish to do something. This is a program called Viewpoints from NASA. This is particularly handy if you're trying to find a satellite, but you don't exactly know where it is. So what you do is you program the dish to swing through the sky and to look around the frequency that you know the transmission will be made on. And then whenever you see it pop up, you can record those times. And this software allows you to deal with large data sets. So you can take all of those spot recordings of, this frequency was in use with this strength at this time for months. And you can take all of the data for those months and sort of work with it until you've identified how to select the satellite you're looking for, and then run it backward through a log from the prediction database to figure out which satellite was in that piece of the sky at that time. Now, I told you that I ran everything through a Postgres database, but I didn't really tell you how the Postgres database could do all of these things, right? Because normally when you do an update statement, that doesn't keep changing future things inside of the database. So I built this all around multiple Unix daemons, which run throughout my home network. I have one daemon that does nothing but orbit predictions. So it will predict where the satellites are, and then it will make an update statement to the database table for every thing that it's tracking. I have another daemon that grabs NORAD two-line entry elements. I have a motor control daemon. This is the thing that actually gives commands to the white circuit board to tell it how far and in which direction to move the motors. I have an inertial measurement unit input, which takes an accelerometer input to tell how high my dish is tilted, and also an integrated accelerometer to tell how far I've moved left and right. And it sanity checks the motor control daemon. So the motor control daemon remembers how far it has moved. Sometimes this isn't accurate. The inertial measurement unit can compensate for that. I also have a radio. I have a couple of different radio daemons because I want to do different things with the radio. For example, I might want to do a spectrum analysis just to tell which frequencies are in use, or I might want to record an individual downlink, and this allows me to do that. Also, because certain other signals are so strong, sometimes I get homesick for my people's native culture, so I can actually download the local FM radio stations and listen to them through the satellite dish. For orbit predictions, I initially used a program called Predict. This is a GUI application, so you have to start it inside of GNU Screen or something else that will keep the graphical window open. It allows you to query the positions of its satellites over UDP, but it's limited to 20 birds. And it can predict some planets, like say the moon or the sun, but it can't predict others. So it won't tell me where Jupiter is or where Mars is. So I switched to a library called PyFM. PyFM allows you to predict the positions of hundreds of different satellites. And it doesn't require any weird UDP tracking. It's just a Python library that you can directly use in a daemon that also talks Postgres. And I can track more than 500 satellites without difficulty this way. It also does planets and stars. This is a test in which I have it predicting every single object that is in geostationary orbit, and also every one of the GPS satellites. These are more than 500 satellites in total, and it's able to predict them without any performance trouble. One of the tricks that I use is I prioritize the satellites based upon their velocity and whether they are being tracked. So if I were to click on one of these satellites in order to follow it, half of the computer's time would be spent tracking just that satellite so that I had it as accurate as I possibly could. But I also need to know what the orbits are, because these orbits change. For really old satellites, things that are just sort of drifting up there, the orbits are consistent. Voyager 1 has no fuel left, so I don't have to worry about Voyager 1 changing its orbit. Updates are published for Voyager 1 once every decade. But I need to be able to track moving satellites, and I need to be able to track ones that change orbit rather often. The International Space Station has a lot of fuel, and it very frequently moves to avoid space junk. So its orbit is very unpredictable. If you were to attempt to do it with pen and paper, you would never be able to keep up. So NORAD runs this project called Celestrak, and Celestrak is a list of everything in orbit. And then they also provide smaller lists based upon particular types of satellites. So if you want a list of every television satellite, or every GPS satellite, or every amateur satellite, you can download these lists and then load them directly into your prediction software. So I have a daemon that automatically grabs these files from the Celestrak server and then feeds them into my Postgres database for prediction as I'm tracking things. The motor control daemon was surprisingly easy to write. The IBOT board shows up as a fake serial port, /dev/tty-acm0. And you can just give it commands in ASCII. So if I wanted to move 500 steps up and 400 steps left, and I wanted to do this in 3,000 milliseconds, I would just run this first command, sm 3,500 -400. And then you send a carriage return, and the motor moves. It sends an OK back to you at the end, and so by waiting on these, you can sort of predict things. But you need to know both where your target is and where your target will be, and in order to track accurately. So moving in 3-second bursts becomes a little bit unpredictable because you wind up moving to where the satellite was 3 seconds ago, which for a very fast-moving satellite can be off by more than half of a degree. You can also enable and disable the motors, and they have different stepping modes. So these are stepper motors, which have many different magnets in them, and you can move a fraction of a step. But if you want to freely move the dish, say to push it around, you need to disable the motors. So one of the things that this daemon will do is it will turn off the motors if I order it to, so that I can physically reposition the dish when I'm debugging things. This is a close-up on rewiring the motors. Do you see that big gray box on the right? That is a 250-watt microwave transmitter. This is one of the stepper motors. These are some of the gear assemblies. So this is a motor on the bottom right. And you can see that it's running through different gears and pulleys in order to increase the motor's strength and decrease its speed. Decreasing its speed also increases its accuracy, which is useful for me when I'm trying to track objects. Now, there's also an inertial measurement unit daemon, which is giving me all sorts of trouble. If I were to build another one of these, I might leave the IMU out. This is the most expensive part of the dish. It cost about $500. I used a VectorNav VN100, which has a MEMS accelerometer, it has a gyroscope, and it has a compass. Now, it's easy with modern MEMS technology to tell how tilted you are, because you just need to measure the direction of gravity, and gravity is very strong. It's a lot harder to measure your azimuth, like how far left and right you've moved, because the magnetic field of the Earth is very inconsistent. Not only does it move, but it's several degrees off from true north, and it's very difficult to work this into your math. And also, it drifts based upon magnetic interference from the motors. And I made the mistake of mounting this too close to one of the motors, so the compass is almost useless. I have to turn off the entire dish and then wait an hour for the compass to become reasonably accurate. And the accelerometer is confused by gimbal lock. So if you have this giving you a vector instead of what's called a quaternion, the device becomes confused if it's pointed straight up. Just like in old jet fighting games, if you try to go straight up. You remember how, like if you look to the sky in, say, Quake 3, and then you turn, you'll spin very, very quickly? That's because when you move your mouse left in Quake 3, you're telling your character to rotate to his left. And if you're pointed straight up, it confuses the software. Now, for position calculations, I take the elevation from the inertial measurement unit Daemon, and I take the azimuth from the motor Daemon. The motor also calculates its own elevation, and this allows me to sanity check to make sure that my motors are not stuck, that I haven't broken any belts. Because when the radio signals stop coming in, there could be a million different reasons for that. And unless you figure out which reason it is, you'll waste hours debugging it, especially if you're trying to debug it from another continent. And I'm not using tilt at the moment. So even though my dish can tilt left and right, I don't have an immediate need for that because I'm using it on solid ground instead of on a ship. Now I have radio daemons, which run through my software-defined radio. There's a spectrum analyzer. This records a given signal, takes the fast Fourier transform, and then it tries to figure out how strong the signal is on each frequency, and also how that strength varies with the error in position. In order to figure out if my dish is just a little bit off to the left or to the right, or a little bit too high or too low, so that I can correct these things afterward. I also have a downlink recorder, and this just takes the raw output from the software-defined radio and runs it directly into a disk, where I can grab it later. But this takes several megabytes per second, so it's not unusual for me to have to download a 2 gigabyte recording, which is difficult to do on a slow cable internet connection in a small town. I'm actually considering putting a bunch of hard disks in a truck so that I can drive the truck to the nearest big city to send the data out to the internet. And these just produce tables within the database that you can query. So there's a spectrum data table that contains the position of the dish, the time, the signal strength, the frequency, and the name of the satellite that I was targeting. And this is enough to figure out whether a signal is spurious, like if it just came on for a little bit, or if it's actually a consistent broadcast of that satellite. This is what I edit with, this is what I view with Viewpoints. Now, Viewpoints presents all of this data as a giant scatter plot using OpenGL. And then you sort of color the points by viewing them from different axes and then selecting the ones that you find interesting. So you can cut out the background noise, find just the signal that you're interested in, maybe divide it into the strong signal and the weak signal, or those sorts of things. And you can view different plots. So you might want to see the time and frequency in order to see how the Doppler shift changes. This will let you determine when the satellite you're tracking was closest to the Earth. You might also look for the received signal strength and the frequency in order to tell which channels are in use, or the azimuth and the signal strength in order to find local interference. So not only can I listen to FM radio with this, but I can also have it swing left to right and tell exactly in which direction the FM radio station is. Now the client GUI is written in Pygame. So it can easily do SQL queries to show the results without having to have any of the satellite logic inside of it. The GUI does not understand that this is a satellite dish. It doesn't understand that it's moving physical motors. All it is doing is showing the results of a select statement and applying the result as an update statement. You could just as easily do this with HTML or JavaScript or whatever tools are common these days. And the server does all of the heavy lifting, which is why it's not a problem for me to run this on my cell phone on another continent, because all it's doing is showing the available data and then applying an update to it. And as I said before, it does it either in a normal view or in a polar view. So at the moment, I have accurate tracking of satellites. I have this operating 24 hours a day for months at a time without the position slipping. So in all of this time, the things that I'm tracking, I continue to track successfully. I have software-defined radio recordings working, but I'd like to do more than that. The next step will be doing a port scan of the entire sky, of every bird that comes over Tennessee. I'm sort of restricted in the satellites that I can view based upon my position. But because I'm interested in moving satellites, I can get a large portion of them. Some satellites will turn themselves off when they're in the wrong position of the sky. For example, Russian television satellites are in what's called a Molniya orbit. They fly very high over the northern hemisphere, but very low over the southern hemisphere. And they only transmit in the northern hemisphere. So I can see them in Tennessee, but you cannot see them in Brazil. And that makes sense, because the intent was for them to be seen by Russia. I also can't see the satellites that stay still on the far side of the Earth. So things that are, say, parked over Asia, I will never see because they never come into my sky. But I can get everything else. And I can take software-defined radio recordings of everything else by first identifying the frequency that they use and then taking a recording on that frequency. The result of this would be several terabytes in size, but it would be one hell of a data set to play with. I'd also like to build other ground stations. So the software should be portable to new hardware, and it should also be portable to having more than one server. And I have a rather large yard, and I can buy more of these things, set them up with antennas on different frequencies, and then have a sort of array of satellite dishes watching the sky. There's another type of satellite tracking that you can play with. This is an amateur radio satellite receiver. This is for lower frequencies, so the UHF frequencies. But it also requires less accurate aim because you're using a directional antenna instead of a satellite dish. And I'd like to build one of these to compare it to my dish and to compare its sensitivity on different frequencies. And I was once told that you should end every lecture with a cat picture. So this is Frank. Turns out Frank was pregnant when we took this photo. So if anyone would like kittens, let me know. Thank you kindly. This is the point where Edmund tells me whether or not I have time for questions. Okay, I do have time. Are there any questions?
Perguntas, galera? No?
Great.
Who needs a shot then?
Who needs a shot? Come on up. Great. Thank you kindly.